All right. So what this problem really means is you're finding the sum of the first 15 terms of the values in this sequence. All right. So, one way to do this would be to list out all of the 15 terms. So the k equals 1 means you're starting with the first term as opposed to starting with some other term, and you're adding up all the terms between the first one and the 15th one. All right. So it kind of tells you where to start the partial sum and where to end it. All right. Usually we do have k equals 1. Sometimes, I might throw on a test k equals 5 or k equals 6. So, you would start with the 5th term and go to the 15th term or whatever. All right. So you could do this the long way and say, okay, plug in 1 and we get 35. Plug in 2 and we get 38. Plug in 3 and we get 41, and so on, all the way up until we plug in 15. So 3 times 14 is 42, plus 35 is 77. Okay, so we're essentially adding up the first 15 terms again in this sequence. All right, in the sequence. But the faster way to do this, instead of just writing down all these numbers and adding them up, is to use a formula. Okay, and just like we've been over in class, we talked about at the end of the second quarter the formula for a geometric partial sum. There's also a formula for an arithmetic partial sum. All right, so now, how would you know this problem is arithmetic? Well, one way is you're just going to be familiar with the notation, right? Like, this is kind of the arithmetic sequence formula kind of embedded in here. But if you're not sure, if you start listing out some of the terms, I don't know if you just noticed this, I erased it, but the first few terms, 35, 38, 41, that I found just by plugging in 1 and then 2 and then 3, this is clearly an arithmetic partial sum where the common difference is 3, right? So if you don't recognize it just by the formula itself, you can write down the first few terms and you would figure it out. All right, but for the arithmetic partial sum, we'll go through this formula a little more formally in class, but just to introduce you to it, arithmetic partial sum, we have n times, so in this case s sub 15 equals 15 times t sub 1. So when you plug in 1, we got, again, 35. Or you might just remember from the sequence formula, that first term out there is always the t sub 1, plus t sub n over 2. All right? So the t sub n part, I actually, unfortunately, just erased this. But that was important. That's really t sub 15, right? You do need the value of that last term in the partial sum. So you do need to plug in. So essentially, we plugged in 1 and got 35. We plugged in 15, and we got, what, 42 plus 35 was 77, right? So that's what we're putting in there. So in these problems, you do need to do a little bit of calculation to figure out the value of the nth term in the sequence, that last term in the partial sum. All right, so we have the first term, the 15th term, add them up, and then multiply by 15, divide by 2. All right, 35 plus 77 is 112, I think. 112, right? We can do this kind of by hand. 112 divided by 2 is 61. No, it's not. It's 56. So we have to do 15 times 56. Well, so 10 times 56 is 560. And 20 times 56 is 1120. So right between 560 and 1120, we'll find the answer. I think it's 840. Right? So the purpose of this one example was to introduce you to the new notation, all right, sigma notation, and also to introduce you to the arithmetic partial sum formula. All right? So we've done that, okay? So if you're asked to evaluate this, this would be the same as asked, okay, to find s sub 15 for the sequence t sub n equals 35 plus 3 times n minus 1. All right, so these are really the same problem. Here you're finding the sum of the first 15 terms in this sequence. Here, it's a new notation, but you're doing the same thing. You're finding the sum of the first 15 terms in that sequence. Did I run out of room here? No, barely fits. All right, let's do one with the geometric. Right. Let's say find the sum of the first, keep it easy, like 6 terms of, let's just do 3 times 2 to the k minus 1. All right, so pretty clearly, if you remember this from the unit on sequences from last quarter, this is going to be a geometric sequence because we have multiplication. If you didn't recognize that, you could just find the first few terms. Plugging in 1, we get 2 to the 0, which is 1 times 3 is 3. Plugging in 2, we would get 6. Plugging in 3, we would get 12. Plugging in 4, we would get, 8 times 3 is 24, and so on, right? So that would be the series that represents this equation. And I mean, we're just finding the sum of the first 6 terms, so of course we could just keep counting, and that's it, right? That's it. The previous problem had the sum of the first 15 terms, so we definitely want to use a formula. In this case, it's just the sum of the first 6 terms. I'd probably recommend the formula is almost more trouble than it's worth. Just find the first 6 terms, those values, and just add them up, all right? Or alternatively, we can use the geometric partial sum formula, which we did do already last quarter, but I'm reminding you of it. It's t sub 1 times 1 minus r to the n, so in this case, 1 minus 2 to the 6th, all over 1 minus r, okay? That formula. So we have 3 times 1 minus 64 is negative 63, all over negative 1. So 3 times negative 63 is negative 189, all over negative 1. So we get 189 as the answer. All right, so just like I showed you with the last problem, another way you could have been asked this problem to do it would be the same, is to find or to evaluate S sub 6 for the sequence t sub n equals 3 times 2 to the n minus 1. All right? So either way, you're asked to find the sum of the first 6 terms, which is called a partial sum. All right? So just want to introduce you to this new notation. You're not going to always just have arithmetic or geometric expressions. You might have something that's totally different, but those, if it's not arithmetic or geometric, you do have to write it out the long way and do it by hand. All right, let's just do one more example, something like that. So here, say k equals 1 to 5 of, say, k squared minus 4. All right, maybe you have parentheses there, maybe you don't. It's not really a big deal. So this one, this is not arithmetic, nor is it geometric. It's just really a quadratic. All right, so you'd have to list these values all out separately. So this would be 1 squared minus 4 is negative 3, right? So our first term is negative 3. 2 squared minus 4 is 0. 3 squared minus 4 is 5. 4 squared minus 4 is 12. And last, 5 squared minus 4 is 21. Right? So we have plugged in 1 to get this, plugged in 2, plug in 3, plug in 4, plug in 5, and then now we would just physically add these up. So that's how you would really have to do this problem. If it's not geometric or arithmetic, you want to really do these by hand. Okay, I mean, there are some other formulas, but they're stuff you'll probably get more into in a future course. All right, so we have 2 and 12 is 14 and 21 is 35. All right, and just to show you, of course, you might notice this, or you might know this from previous conversations we've had, but in a quadratic, there is a pattern here, right? In this case, we've increased by 3, and then by 5, and then by 7, and then by 9. That is a characteristic of quadratic relationships. There's an increase in consecutive odd integers, all right? So hopefully this was a good introduction to sigma notation and how to use these two formulas for arithmetic and geometric sequences, and also to Greek life at Vanderbilt University. All right?